Okay, I suppose we'll get going. Because, knock on wood, fingers crossed, I would like to be done lecturing today, content. Worst case, I might have to spend like a little bit of time on Wednesday, but that's the hope anyway. So last class we talked about matrix operations and matrix multiplication. Operations would include, addition, subtraction, scalar multiplication, that sort of thing. But then we do actually have a concept of multiplication, and I presented it 3 different ways. One was just the strict formula, which you could use if you want. It's not very human readable, but it's good for computers. Then I sort of showed you, okay, here's how the formula works, but then I showed you, you can use your fingers to sort of navigate matrix multiplication, and that's what most people end up doing. But there is also a dot product interpretation of it. If you write down all the rows of a matrix and all the columns of the other matrix, then the entries are just the dot products of the corresponding rows and columns. So that's another way to do it. So there's 3 different ways to do it, and we're going to get lots of practice going through it with examples. But going through the quiz from the one that was just due, it was all row reduction and that sort of stuff. Everyone did fine on it, so like it's yeah. This is again, these are the topics where it seems like it's really confusing and there's a lot going on, and then everyone actually sits down to do it and they're like, oh, it's not that bad, right? So it's like minor arithmetic mistakes. Otherwise, it was good. So one thing I do want to mention real quick, related to matrix multiplication, is we do have the concept of taking the power of a matrix, because now we have multiplication, so we can take the power of one. And it's what you would expect. So first, just like with numbers, if we raise it to the 0th power, it gives the identity. And if we raise it to the power k, where k is some, k is positive number. Let's say not number, integer. We have to be very careful here. And this is just a times a times a k times, right? It's exactly what you'd expect it to be. Just like with, 2 to the power 4 is 2 times 2 times 2 times 2, right? This is a to the power 4 is a times a times a times a. Now, when we're talking about powers of numbers, though, we can talk about negative exponents, fractional exponents, etc. Not really with matrices. Positive only right now, because a negative exponent would be 1 over a matrix, and we'll get there. So there is something kind of useful matrix multiplication thing, and is that there's a shorthand way of writing down an equation. So let's say the equation, I'm just going to write down an example because I have it written down in my notes with the general stuff. So let's just x minus 2y equals 2. So we've got this equation, right? So we know that we can write this as an augmented matrix, right? So we could write this as 2, 3, 1, 1 minus 2, 2, right? We're used to this. So this chunk right here, we call that A, and this little chunk here, we call that the vector B, right? So we can actually recontextualize this equation in terms of matrix multiplication. So if we just say, okay, it's going to be A times something equals B. So what is that something? It actually ends up being really easy. We're going to take a vector x, which just contains our variables. So this is going to be 2, 3, 1 minus 2. This vector here is our variables, so x, y equals 1, 2. So if we actually perform this multiplication, we would get 2 times x plus 3 times y equals 1. 2x plus 3y equals 1. That's the first equation. X minus 2y equals 2. This is the second equation, right? So it's just another way of writing it. And this will end up being useful because if we think about equations, like if this were an equation with numbers, let's say we're like 5x equals 3. Well, there's a pretty natural way to solve that, right? Divide by 5. So if we could do that for matrices, then writing an equation this way gives us an easy way to solve it. But then we have to figure out what does it mean to divide by a matrix, and unfortunately, it turns out that doesn't make any sense. So now that we have these operations, we can talk about various properties. So I'm going to say for addition, works how you hope. So what I mean by that is a plus b for matrices is the same thing as b plus a, right? Stuff like that. So an example, a plus b is equal to b plus a, and that's true for subtraction as well. Another example, a plus 0 is a, right? All this kind of stuff works how you would expect. If you have a number, sorry, I'm going to use s for scalar. A plus b, it works how you would expect. So s times a plus s times b. These are scalars now, that's why I chose s. So the punchline here is that everything works how you would expect, right? No surprises there. Now, the secret with matrices of multiplication does not work how you would expect because of one specific property. So there are still lots of properties that work how we expect. So one of them is if you have brackets, they don't really matter. So you could do that sort of you could do a times b and then multiply by c, or you could do b times c and then multiply by a, right? Those are fine. Either will give you the same. It does interact nicely with addition. A times c, so that's distributive. Of course, I did mention this. The identity times a is equal to a times the identity, which is just a. It works as 1. Nothing happens there. But there's a property that I always write down that I haven't. So a times b equals b times a. No, not for matrices. In fact, almost never. If you pick 2 random matrices, they're not commutative, almost ever. The only matrices that commute with all other matrices are just the identity times a number. So it's like really boring matrices. So that's something to be careful about. So when we're talking about how it's not true, I should just give you an example, right? Like I said, just random matrices will probably not work. And I'm so confident in that. I have an example in here. I'm going to pick different numbers. So a times b. Well, let's say a is 1, 2, 3, 4, and b is -1, 2, 1, 5. I hope that's not a horrible number for me to work with. But this doesn't match the example in my notes. And it would be really funny if this happens to be 2 matrices that commute, in which case I just pick another 2 numbers. It doesn't matter. But unlikely that they do. So let's actually figure out this product. So a first times b. So we go ahead and we go through the motions, right? This is -1 plus 2. So that's 1. 2 plus 2 times 5, so 2 plus 10 is 12. -3 plus 4 is 1. So this is 6 plus 20, 26. Right, so this is just the finger motion for multiplication. Well, that's what a times b is. What about b times a? Other way around. 2, 5. 1, 2, 3, 4. So minus 1, so that's minus 1 plus 6 is 5. I didn't need to go any further. They already don't match, right? So the literal first entry in these matrices, when we swap the order of multiplication, they don't match. But let's just keep going. So minus 2 plus 2 times 4, so minus 2 plus 8 is 6. 1 plus 15 is 16. And 2 plus 20 is 22. They're not a single entry matches, right? In fact, there's not even any repeated stuff. So like it, just a random 2 matrices I cooked up, they don't commute, right? So this is a warning. Almost never is this true. So A times B is not B times A. In fact, this is almost never true. So it's sort of like that that phrase, I before E except after C, is actually false more often than it's true. This is another situation like that. If you find 2 matrices that commute, you got extremely lucky. Pick another 2. They don't. But that means certain things in algebra that we're used to doing don't work. So if we have something like this, A minus B times A plus B, we're so used to, if we have done this a lot in high school, we're so used to doing it a certain way, where we would go, okay, well, I can FOIL this. It's going to be A squared minus 2AB plus B squared, right? No. It's A times A. So A times A is A squared. That's okay. Then it's A times B. Then it's minus B times A minus B squared. Sorry, I should have been, yeah, minus there. These 2 things are not the same thing. We can't just combine them. We can't just suddenly swap those things, right? And make things work out nicely. So you have to be very careful with these matrices, right? You have to pay attention to the order in which you're doing things, which is a bit unnatural at first, but it is something that you get used to and just comes with practice, right? But basically, because this property fails, a bunch of other weird stuff happens with matrices. So, more fun stuff. I think it's fun anyway. I think it's neat. Math is all about finding when things fail. When everything works nicely, it's not that interesting, right? You know, my mom thinks that I went to university to study arithmetic. Like, no, we've known arithmetic for hundreds, if not thousands of years. I didn't go to school for that. I went for school when do those things not work anymore, right? That's the interesting stuff. So an example, if A times B equals 0, well, with numbers, we're used to saying, so if you had X times Y equals 0, that means either X or Y is equal to 0. One of them has to be 0, right? That's not the case with matrices. It doesn't mean A equals 0 or B equals 0. So what that means is there are matrices A times B that equal 0 where neither A nor B is 0. And actually really simple ones work. And there are more complicated versions of this. So that's what I'm choosing for A. Obviously not 0. And then I'm going to choose this for B. Also obviously not 0. Actually, make sure that works. Yeah. Wait. No. I need to do this. There we go. That should work. No, it doesn't.
You want the one on the
I want it
on the bottom left.
Yes, like that. There we go. Okay. We got there. So let's actually compute this. So 1, 0, 0, 0, 0, 0, 1, 0. So if we actually do this, we get 0 plus 0, so that's 0. 0 plus 0 is 0. 0 plus 0 is 0. 0. Got everything was 0. But neither of these matrices are 0. And these are simple looking ones, but you can find matrices that aren't simple looking that satisfy this property, right? So we can't take this for granted either. So because of that, that means we can't cancel things, right? The cancellation law doesn't hold. So this means we can't cancel matrices. So what I mean by that is if you have A times B equals A times C, does not mean that B equals D, right? Because, let's take a look at this. Well, if we move everything to one side, we get that equals 0. One of our properties for matrix multiplication, at the very least, is if these are on the same side, we can pull them out, right? So this would be A, B minus C, because we can just distribute this back in, right? A times B minus B, A times C, same thing. But now we know this does not mean that A is 0 or B minus C equals 0, which would mean that B equals C, right? So that's something we can't do either, right? We're so used to that. If you have 5x equals 5y, you cancel the 5s, right? No, not with matrices. Okay. There are some other, there are more weird ones. We actually, they come up often enough that we give them special names. I don't expect you to know the name. I write down the name in an assignment and then I'm like, by the way, that's what this means, right? I don't expect you to remember these. So there are non-zero matrices A, where A to some power equals 0. So if we think about numbers, if we take any number and raise it to a power and get 0, there's only one number that satisfies that, right? 0. If you take any other number and raise it to a power, you're just going to get another number that's not 0. But again, matrices, not the case. So let's let A be, well, technically I can put any number I want here. Let's call it Jordan block, and this is actually an important property of them, is that this happens. So A squared, so A times A, 0, 3, 0, 0, 0, 3, 0, 0. Well, given the context here, you probably know what's going to happen. 0 plus 0, so we write down 0. 0 plus 0. 0 plus 0. 0 plus 0. So we got the 0 matrix, right? So these matrices, they have a name. They're called nilpotent. Again, I don't care if you remember that name. I'm just writing it down for posterity. So that's already kind of weird. There are things where when we raise them to a certain power, we get 0. Another one, and I could come up with weird matrix trivia all day, honestly. And all of this comes from one property that would take for granted not being true, right? So there are also matrices A that aren't the identity or 0, where A squared is A, right? So we think of numbers. The only numbers that satisfy, if you square it, you get the number back is 1 and 0. 0 squared is 0, 1 squared is 1. But everything else, if you square it, you're going to get either a bigger or a smaller number, right? The number's going to change. But matrices, not the case. This one I'm going to be very careful about copying down. So let's let A be this matrix. So this is something that isn't just like, a bunch of zeros and one number. I actually have numbers here. You could probably spot the important distinction between the rows here, but So we're going to take this thing and we're going to multiply it with itself. And what do we get? Okay, well, I have to do the math now, unfortunately. So we've got 4 times 4 is 16, minus 12 is 4. 4 times minus 1 is minus 4. And then this becomes plus 3, so minus 1. 12 times 4 is 48, minus 3 times 12 is 48, minus 36 is 12. Minus 12 plus 9 is minus 3. Got back where we started. Right? These matrices are called idempotent. And no, in math, we don't come up with names for things that just to huff our own farts or anything like that. We do this because they come up all the time, right? So these types of matrices are everywhere in terms of places where you would care to study matrices. I mentioned that something that's shaped like this actually, this shape, not just nilpotent, but this specific shape of like 0 all below the diagonal and then numbers above it is called the Jordan block. It actually has a name too. It comes up all over the place. So these are just weird situations for matrices, right? So I kind of just wanted to emphasize that matrix multiplication is weird. So that means if you're doing a problem that involves it, by which I mean either in this course or you have run into some kind of real world problem that requires you to work with them, like if you're dealing with physics or geometry or something like that, image manipulation in a back end, you will probably be dealing with matrices and you might have to multiply them, especially if you're doing rotations. Make sure that you pay attention to the order in which you do them, because that actually matters. And if we're talking about rotations and sort of like stuff like that, like graphical transformations, it even kind of makes sense, right? If you rotate something, let me think, can I think of an example? You rotate something 90 degrees to this, and then mirror it along a specific axis, you'll get something different than if you did it the other way around, right? So it kind of makes sense from that sort of transformation perspective, right? That the order in which you apply transformations will change what it looks like. Okay. So matrix multiplication is weird, but this is what I'm talking about with math, where the interesting stuff is when things are weird, when things don't work how you expect. That's, because that leads to questions like, okay, so this doesn't work. But man, that sure is a nice property, right? Like it really is nice when we can do this. So now a natural question for matrices is like, okay, I can't do this all the time, but surely some of the time I can do it, right? Some of the time I can cancel this out and then I will get that B equals C, right? If the answer is no, then that's also interesting, so we should check. So it turns out the answer to that is sometimes yes. Actually, interestingly, I say that almost no matrices commute, and I say, hey, this is not true most of the time, it's not true all the time. This actually does end up being true most of the time, because there's only one specific situation in which it's not true, and it is something that you can easily calculate in advance. But some things for matrices are true all the time, or most of the time, and some of them are true almost never. So we can get something like that using what's called the inverse. And technically, the inverse of the idea of an inverse is nothing new. You've been doing it all your life in math. Well, maybe not all your life, since when do they teach fractions or division? I don't know, grade 5, who knows? So you've been doing it that long, right? That's the idea of an inverse. So we're going to write down the definition first. So let A be some matrix. So an inverse of A is some matrix B, squeak, such that A times B is the same thing as B times A. So already that's nice. Which all equal the identity. So when you multiply them together, you get essentially the 1 for matrices. So it turns out this inverse is unique. So there's only one. And we denote it a to the negative 1. So this actually matches numbers because we this notation here, this you probably don't remember, but if we can write 5 to the negative 1, right? I don't remember what that is. If you don't, it's fine, but just curious. No, but kind of you're on the right track for thinking it does do something to the number. Yeah.
It's like 5 to the 1 over.
It's 1 over 5. Yeah, yeah. So this notation is saying, hey, it's 1 over 5. And if we think about it, the matrices were saying basically that A times A inverse equals some form of 1, right? So the same thing is happening here, right? The number 5 to the negative 1 times the number 5 is 1 over 5 times 5. They cancel out, you get 1. Right? So this is behaving the same way as numbers, but with these new objects, right? This is capturing that same idea. Right? Again, this notation is something that you would only use when you're going into like calculus and stuff like that. So even if it was mentioned to you, it would have been like, yeah, whatever, forget about it. So that's why I'm like, hey, like this, you might have seen this notation and then just pushed it out the other end of your head, and that's fine. But I'm just drawing attention to the fact this is kind of what we're trying to do with matrices, right? We're trying to essentially get some form of fractions or something that emulates fractions. So let me just show you a quick example to at least convince you that, yes, these things do exist. So let A be this matrix, and I have to be careful about what I write down. We're going to say A inverse is this minus 3, minus 1, and 2. So if I'm saying this thing is the inverse of this, that means when I multiply them together, I better get the identity, right? So I'm going to write this here, A inverse, because we're saying that's the notation we want to use. So let's see what happens. We multiply these two matrices together. 2, 3, 1, 2. 2 minus 3 minus 1, 2. Well, we crunch the numbers. 2 times 2 is 4. Minus 3 is 1. Okay. 2 times minus 3 is 6, or negative 6. 3 times 2 is 6. They cancel out. You get 0. 1 times 2, so that's 2. Minus 2, you get 0. 1 times minus 3, so that's minus 3. 2 times 2 is 4, you get 1. So we actually got the identity, right? So this does do what we want it to do in the sense of getting us some kind of fraction-like thing. Okay, but how do we find it? Because for numbers, we look at this and I'm like, hey, you know, now that I've told you this, if I said, okay, go find the inverse of 12, it's like, okay, it's 1 over 12, right? We don't have to really do anything. Now you know how to find it. But, you know, I wrote down this matrix. I'm like, find the inverse. You'd be like, you already did it for me, Travis. Thanks. And if I wrote down a different matrix and said, okay, go find the inverse, you'd be like, I guess I'll just guess and check for a while, right? But thankfully, no, we don't have to do that. So the inverse for 2 by 2 matrices is a formula. So that's quite nice. So A inverse. So we basically just have to swap some stuff around, thankfully. So we're going to swap the diagonals around like this, and then we just put minus signs in front of the other entrance. But we have to have a fudge factor here. So there is an extra thing that you kind of do at the very, very end. So it's AD minus BC. There's this number here, right? That's a number. But this is just a formula, right? Your entries of your matrix A are this, A, B, C, D. If you know that, you plug it into this formula, boom, there you go. There's your inverse, right? Nice little formula for it. This thing right here, it has a name, which is outside the scope of what we care about, because you could spend like a month talking about determinants and their properties. This is one of the other operations we can do on a matrix. But if we look at this formula here, we can kind of anticipate the situations where this inverse wouldn't be possible, right? If what's in this denominator is 0, then we have a problem, right? So it turns out that matrices don't have inverses when this quantity here is 0, and for bigger matrices, this idea of what's called a determinant is 0. That's when we don't have inverses, which that means there's one number that this can't be, which means there's infinity numbers it can be. So that means most of the time a matrix will have an inverse. It's probably hideous. If you write down random numbers for a matrix, it's going to have horrible fractions and decimals in it, but it will exist. Okay. So why would we care about this, right? I did mention that it lets us essentially use cancellation, right? We can cancel stuff, right? We just have to multiply. Like if we multiply by this A inverse thing, it cancels with A, right? It'll turn it into the identity and then nothing happens. So if A So if A is what's called an invertible matrix, namely A inverse exists, so we can find it. We have a system of equations written as A times X is equal to B. I just sort of mentioned that, hey, we could write an equation like this too, right? Remember, this is the coefficients. This here is the constants on the other side of the equal sign, just like in our augmented matrix. So the only new piece here is this X, which is just a vector of variables. Well, if A inverse exists, this is just an equation. So that means as long as we do the same thing to both sides, we're allowed to do it. So if we multiply on the left by this thing, it'll cancel that A and we'll just get that X equals stuff, which sounds an awful lot like we just solved for the variables, right? So multiply this equation by A inverse on the left, and this is an annoying part about linear algebra. You have to always specify that because multiplying it on the right will do something different. So we're going to get A inverse times A times X is equal to A inverse B. These cancel out, right? This works how you would expect it to. A inverse B. This just becomes X, which means this right here is our solution, right? Because we just said the variables equal some numbers. This is our solution. Okay, well, that means, though, that if we can find this thing, this A inverse, and we just have to multiply it by this vector here, which we just read off from the equation, and then we have our answer, right? And that would skip us a lot of row reduction, right? Because we went through that whole process of like, okay, how do we solve these systems of equations? Well, we do that row reduction business. So you know, if we can find this inverse, then we can skip doing row reduction. Bad news. How do you think you find the inverse? You use row reduction. There's technically another way to do it, but it's actually worse. This is something that, so if I'm mentioning this for the video, and I guess anyone in here, if you know the method of using minors and determinants, don't use that method for many reasons. One, I didn't talk about it, so you better be able to explain to me the formula for a determinant and what it means and where it comes from, if you're going to use a method that I didn't talk about. And also, two, it's more inefficient the larger the matrix is. So if you have a 5x5 matrix and you try to do that method, you will have to compute an ungodly amount of determinants that are all really horrible. So please don't use that method. Trust me, row reduction is the better way. So then if I'm saying, well, you're going to have to do row reduction anyway, why would you use this? Well, it's not uncommon to have a system of equations like this. You've got your coefficients here, and then you've got this variable here. Your variables are always the same. And this thing here, you change, right? Because these are sort of like the parameters of your system, right? These are, you know, what goes in front of the variables that describes how everything interacts. And this is saying, hey, this is the expected result, and you vary that. So if all you're varying is this, then you just have to do a bunch of matrix multiplication to get different solutions, right? So if you have to solve the same thing multiple times, but with different right-hand sides, then it's very efficient. Because otherwise you have to do row reduction every single time. And that's decently common in like physical systems where that's the thing that you're varying, is like your expected coordinates or something like that. Okay, so I have a bunch of boring proof stuff in here. So let's just do an example. Especially with 2x2 matrices, it's pretty nice because there's just a formula for it, right? So we just plug and chug. So let's consider the system. 4x plus 3y is equal to 1. 3x plus 2y is equal to minus 1. Okay, so you could find the augmented matrix and then do your row reduction. That's fine. But let's take a crack at this. So we know that A is just these coefficients like it was before. So it's almost like writing down the augmented matrix, you just don't write that last part. Although you still do, you just write it separate. So now what we need is the inverse of A. Because if we know the inverse of A, it's going to go right here. It's 1 minus 1. Right? If we just know what that is, we just plug it in, right? And we're good. So what's A inverse? Well, there's a formula for it. So it's 1 over AD minus BC, DA minus B minus C, like that. So we just plug in, right? A is the top left number. So 4 times 2, because D is the bottom right number, minus 3 times 3. And then now we do the shuffling. Bottom right number becomes top left. Top left number becomes bottom right. And let's put minus signs in front of these. Okay, well, unfortunately, this means your inverse often has fractions. Again, I try to avoid it. So this is going to be 8 minus 9, so it's minus 1. Hey, that worked out. Because it's 1 over minus 1, so that's minus 1. 2 minus 3, 4. We just multiply everything by minus 1. And boom, there's our inverse, right? So I'm writing everything out in gory detail, but like stuff like this, if you were to actually deal with it, people just do in their head, right? Once you get enough experience with these matrices, it just kind of happens. But now we know what this thing is, right? That's what we just found. So minus 2, 3, 3 minus 4 times 1 minus 1. So we just go ahead and do this multiplication. minus 2 times 1 is minus 2. 3 times minus 1 is minus 3, so minus 5. 3 plus 4 is 7. Bam, there we go. There's a solution, right? So the reason why this is nice, again, it's just a formula, right? You just plug it in. We basically just have given a formula for solving 2 by 2, or 2 equations with 2 variables, right? There's just a formula for it now. Downsides for this, inverses are only defined for square matrices. So, I guess I'll put that here. So that is a limitation, right? That's something that, well, if it's not square, then that means you have to go back to old methods. But if it is, it's very fast. So note, inverses. So this idea of A inverse only exists for square matrices. Unfortunate. Okay. So now we know how to find it for 2 by 2 matrices, right? So I've kind of buried the lead here. How do we find it for something bigger? Well, it just boils down to row reduction. Yep.
Where did the minus 1 come from? At the bottom right. Minus 1 times.
Right here. So this is this number right here. So I'll put it up here. We got this fraction part of the formula, 4 times 2 minus 3 times 3. So that's 1 over 8 minus 9 becomes 1 over negative 1, which is negative 1. Yeah, that's where it came from. Okay, so how do we find this for bigger matrices? This work. Or larger matrices. I can't spell. Good news. Row reduction. So in my notes, I explain essentially why. It's ultimately because if A is invertible, its reduced row echelon form has to be the identity. Which it turns out that means those same row operations will transform the identity into the inverse if you just do the same thing. And actually, this is called the fundamental theorem of invertible matrices. And there's like, I kid you not, like 24 different conditions to say a matrix is invertible, and they're all varying levels of useful. But the point is, how do we do this? So we write down the matrix. So we're going to write down our A, right? And then just like we do with systems of equations, we're going to write a slash. But instead of putting just a single column, we're going to write down the whole identity matrix. And what are we going to do? We're going to focus on A. We're going to say, okay, I'm going to row reduce so that this A is the identity. But this is still one big matrix, so everything I do to, row 1 here has to happen over here as well, right? And I'm just going to keep going through that, and over here, I will do row ops to get to, well, this will be the identity, and then what's over here? A inverse, it turns out. So if A is invertible. But the nice thing is if it's not, we also find that information out. Because what will happen is we'll start with this, and we'll perform our row operations. And what are we going to get? Not the identity. By that, I mean there's going to be a row of zeros. So then, what is over here? Junk. Doesn't even matter. It's meaningless. It's not the inverse. Not inverse. So what does that mean? If a question says, by question, again, I mean, when I present it to you or if you ever run into it, if it says, you know, you need the inverse of this if it exists, then how do I know it doesn't exist? You go through this algorithm the same way, no matter what. If you detect a row of zeros, you can be like, I don't have to go any further, right? So row of zeros in A part means stop. You're done. No inverse. So it's another one of those algorithms where it sort of answers two questions at once, right? If a question says, is this invertible? Well, I'll just go try and find it, right? Either I'll find it or I won't. So let's go ahead and do an example real quick. So let's let A be the following matrix. And again, I have to be careful. I mean, I should be careful all the time, but I like to live dangerously. So we've got this matrix. Now, again, just like with solving systems of equations, your final answer should not have fractions in it, unless I've made a horrible typo. But generally speaking, I try to do it in a computer for something like this. It's possible. I mean, so usually typos that cause problems would be because the same thing is written in two different places, like what happened 2 quizzes ago. But this one, I would just write down the matrix once, so it's probably not going to happen. However, that does mean, again, just like with row reduction, if you could have fractions along the way, that's up to you. It can happen. It's not wrong, but it can happen. But in this one, it's going to be pretty clear what we need to do. So let's find the inverse. And there's no shot I have enough space to do this. So we'll have to move over to here, I'm sure.
Thought you removed that thing for the screen today.
Yeah, and then I didn't. Look, do you know how hard it is to break a 3-month habit?
Yes.
Yeah, it's pretty hard. So, that thing where I even like before I came into the office, I was like, I'm gonna do that today. No. So anyway, we always start the same for finding an inverse. We're gonna write down our matrix A. We're gonna do the slash, and we're gonna write down the identity. So what does this look like? So we've got our A, and then we've got the identity, which is this matrix, right? It's the diagonal of zeros or ones and zeros everywhere else. And now, like I said, our goal is to reduce this left-hand thing to the identity. Right? That's our goal. This thing is going to come along for the ride. So let's do that. So we could do row 2 will become row 1 or row 2 minus row 1, and row 3 will be row 3 plus row 1, right? Okay, so that's going to do nothing up here. So now it's a row with 6 columns rather than a 3. What happens here? This becomes a 0. This becomes a 1. It's a minus 1. And now this is the thing that is easy to mix up. You have to keep going, right? There's still more. So this subtracted from here is minus 1, 1, 0. Now we took this and added it here. 0, 1, 0. 1, 0, 1. All right, and then we just perform the process, right? We say, all right, we dealt with row 1, and now we repeat, right? Grab the top leftmost thing and make zeros below it. Now, there is a little trick you could do here, though, because remember, our goal is to get not only that staircase thing, but zeros above and below everything. So this row here is already pretty nice, right? It's got zeros everywhere except one spot. So I'm going to swap it with row 2. You don't have to do this. It would still work out just the same. In fact, what do I do in my notes? Do I do that swap? I don't. So in my notes, I don't do the swap. I just keep going as natural. So let's try that swap so we get something different. Row 2 swap with row 3. Again, just to emphasize that there's lots of different ways to do it. 0, 0, 0, 1, 0, 1, 0, 1. Minus 1, 1, 0. Okay, so now we just have to use this to get rid of that below. And actually, we can also use it right now to just get rid of what's above too, right? We might as well. If you want to just keep going through the algorithm, that's fine. I just want to save space because I'm running out. So we're going to do row 1 will become row 1 minus row 2. And row 3 will become row 3 minus row 2. What's going to happen? This is a 0. 0 minus 1. That becomes 0. 0 minus 1, it stays as 1. But now this is a little different. So we've subtracted this row from this one. So this is going to be 0, 0 minus 1. This stayed the same. This row taken away from that one. This row taken away from this one. So minus 2, 1, minus 1. And now we're almost home free, right? Take this and add it up there. Row 1 plus row 2. 1, 0, 0, 0, 1, 0, 0, 0, minus 1. And that will be minus 2, 1, minus 2, 1, 0, 1, minus 2, 1, minus 1. And then just minus 1 times row 3. Because we got that minus sign right there. Yep.
You have row 1 plus row 2, but wouldn't that make row
Oh,
1?
right. Sorry. Yeah, this is row 1 plus row 3. Thank you. Where we're taking this and using it to make a 0 above. I'll even like that. Okay, so the last thing, we just have to multiply this by minus 1. 0, 0, 1, 0, 0, 0, 1. Look at that. That's the identity, right? That's our goal. Minus 2, 1, minus 2. 1, 0, 1. 2, minus 1, 1. Which means identity inverse, right? And we can double check that. That's the nice thing about these sorts of questions, that it took me way too long to realize it when I was learning it, because my instructor never told me. But all these things are self-checking, right? So like you solve a system of equations, well, plug your answer in to see if it works out, right? It should solve the system of equations. You just found the inverse of this thing. So, okay, this thing times that better give us the identity, right? If it doesn't, then I made a mistake somewhere. So A inverse is what I have there. Just make sure I didn't screw it up. Nope. Minus 2, 1, minus 2, 1, 0, 1, and 2 minus 1, 1. Like that. So let's check. A times A inverse. I already forgot what A is. 1, 1, 1, 1, 2, 0, minus 1, 0, minus 1. Times this thing. Minus 2, 1, 0, 1. All right. Bunch of 1s and 0s and 2s. But let's check. So it's a little harder to do 3 by 3 or bigger matrices in our head, but let's give it a go. Minus 2 plus 1 plus 2. So minus 2 plus 3 is 1. 1 plus 0 minus 1 is 0. Minus 2 plus 1 plus 1 is 0. Minus 2 plus 2 is 0 times 0 is 0. 1 1. Minus 2 plus 2 is 0, and then times 0. 2, 0, minus 2 is 0. This and that is 0. And minus 2, plus 2 minus 1 is 1, right? So it works out. I went through that kind of fast because I already know that the answer is going to work out. But you can check them, right? That's the point. Is this is what it should look like, right? If it doesn't, then you made a mistake, right? So this is something that is interesting. Let's say you go through this. This was especially true when I was teaching engineering, and they had to do a lot of really nasty stuff like this, like really horrible numbers. I was like, yeah, self-checking, right? You could check your answer. So let's say you did do this though, and you didn't get the identity. You're like, I screwed up somewhere. You know what's actually worth marks? If you just do this and say, clearly I screwed up. I don't have time to fix it, but like I recognize that I made an error. This is not correct. I'd be like, hey, that demonstrates understanding, right? You know it's not correct, so that is worth something, right? So I'd always give like a bonus 0.5 or 1 for students who did that. It's less, I mean, I would still do that here, to be clear. But the numbers work out nice. Like they had to use MATLAB and stuff like that, so they would get like really disgusting, like, you know, they would work by like 9x9 matrices and just really horrible numbers. And I was like, okay, you know what? Like, one of your columns is incorrect and you recognize that, that's good enough, right? So for us though, I try to keep sure that the numbers are nice. So then I have a bunch of properties of invertible matrices that I think we just don't even really care too much about. These are some warnings about inverses, because this is just like row reduction, right? You do this once or twice, they're all the same, right? I could give you a 6x6 matrix and you would give me the middle finger because you'd be like, this is the worst thing you've ever made me do. But also it's the same process, right? It's like, it's not, there's nothing that can trip you up with it. So, warnings. So the first one is, I would say it's probably the most common thing that students get wrong. You need to write A inverse, not 1 over A. So what I mean by that is you can't write B over A. Because which side is A inverse coming from? Left or right? This notation doesn't have any indication, right? It's not clear. So does this mean A inverse B or B A inverse? They will almost guaranteed be different answers, right? So this notation is incorrect. It doesn't make sense here. So yeah, it seems a bit uncomfortable to have to write this all the time, but it is what it is. And these are things that aren't true for numbers either, but I see students make these mistakes all the time. And then I ask them, you know, what if I replace these with numbers? And then shockingly, they say, I think it still works. And I'm like, you should check that. So A plus B is not necessarily invertible. And my point here more is that these aren't true for numbers either, so we shouldn't expect them to work here. Although it's fair to say, well, just because it doesn't work for numbers doesn't mean it suddenly doesn't work here now. But if we think in terms of numbers, 1 plus -1 is 0, so you can't divide by the result of that. So same thing here. This is not necessarily invertible. And I have some examples in here if you want to be convinced. But this is the more important one. Even if A plus B is invertible, A plus B inverse is not A inverse plus B inverse. Right? There's no easy way to find the inverse of a sum. This isn't true for numbers either. So we shouldn't expect it to be true here. So if you just think about it, 2 plus 2 inverse. So is that the same thing as 2 inverse plus 2 inverse? Remember, this just means turn it into a fraction, right? So this right here is 1/2 plus 1/2 is 1. Okay, well, what about over here? This is 4 inverse, which is 1/4. Definitely not 1, right? So it's not true for numbers either, even remotely. In fact, the only time this is true for numbers is if one of the numbers is 0. So it's generally not true. But that means it's not true for matrices either, right? And in the notes, I basically present the matrix equivalent of this example, right? If you take the identity and add it with itself, its inverse is not the sum of the inverses of the identity, right? So what I mean by that is try A equals this, and B equals this. The inverse of A is just A. It's just the identity matrix. So this side would be this thing plus itself, which is 2, 0, 0, 2. And then if we try to find the inverse of this added together, which is 2, 0, 0, 2, it ends up being these switched to 1/2. So they don't look the same. So it doesn't work here either. Let's see. This is sort of just like a puzzle example, and it's the last thing I'm going to talk about, right? And then you're not free from math. Sorry, programmers, you'll never be free from math. You'll probably be free from theoretical math, but I can't guarantee that either. Unfortunately, as we march ever towards the future, computational efficiency becomes more and more important, which means you'll need to know algorithmic efficiency of the various things that you're dealing with, especially with large data sets. So that will all matter. Okay, so this is just kind of like a puzzle. I might have a similar example on the assignment, so I just want to go over it. So let A be an idempotent matrix. And like I said, I don't expect you to know that. So A squared is itself. So verify that I minus 1/2 A is invertible with inverse we'll say it's I minus 1/2 A is I plus A. So this is a whole lot of words, right? But the key here is it says verify it's invertible with a given inverse. So there is an important part of this definition. What does it mean to be an inverse? It means, hey, we're saying this thing right here is the inverse of this thing. So when we multiply them together, we should get I, right? This means I minus 1/2 A times I plus A should equal the identity. We just need to check that, right? We're just going to have to do some algebra. So, okay, we're going to FOIL. And foiling works exactly how you would hope it to. The only difference is A times B is not the same thing as B times A, so you just have to pay attention to your orderings. So this is I times I times A, minus 1/2 A times I minus 1/2 A times A. Okay, but fortunately we can do some simplifying here. So I times I becomes I times anything becomes itself. Same thing here. 1/2 A. And this is minus 1/2 A squared. But we know something about this matrix. We know that A squared is A. Oh, yeah.
How does I times I equal I?
So you could think of it a couple different ways. So I times A, we know is A, right? Because it sort of acts like 1 for multiplication. So that means I times, if this is I, then we just write down that I, right? It just gives us back the thing on the right there. You can also actually just do the multiplication. So for a 2 by 2 situation, we've got this, and it will be true all the way through. So this is 1 plus 0 is 1, 0, 0, 1. And it ends up giving us the identity. So this is called the fundamental property of the identity of multiplication. It's just if you multiply anything by the identity, it just gives that anything back. And in this case, the anything just happens to also be the identity, so it works out. Good question, though. So now we're just going to use this fact, and this is, so far all we've done is we've just done algebra, right? We just did FOILing. We haven't used anything special to the question. So now we're going to use this fact. We know A squared is A, and we have an instance of A squared here. So let's replace it with A. Minus 1/2 A. And now we have a bunch of A's. So we can actually collect these together. Plus A minus 1/2 A minus 1/2 A becomes minus a full A. These cancel out. And we get the identity, right? So that means this thing times the thing that we said was the inverse. We do algebra and we get the identity. Right? So then that means this thing is indeed the inverse of this. So this is just sort of like a bit of a puzzle. And it's an insight into what my life was, in the sense of the puzzle was just there was something stated in the question, but in my case, in some other paper I read. So I just have to go dig up that paper and go, there it is, and then I, credit the source and write it down, and I say, because of this paper, I have this result, and I continue. And it was dreadfully boring. I love math. I hated getting a graduate degree in it. It was a lot. But anyway, I think maybe I took it out, maybe I didn't. I should have checked before I came in. But just in case, there would be if there is a similar question, it would be the same thing, except these are like slightly different numbers, or it's the same idea, except instead of idempotent, I said it's nilpotent. By the way, that means A squared equals 0 or whatever, right? And then you just do the same thing. So anyway, I guess that's all. I'm done, math. Yay! You're not celebrating me. You're celebrating being done math. But I'll take it anyway. So I guess quick announcements. There is no quiz this week. That by the letter of the law, aka the course outline, it does say that there is a chapter review assignment due on Saturday. So what I did was I just took the quiz and made it the chapter review assignment. So it's like 2 questions. So it's really, really short. And I think it's literally just solve this system and then find the inverse of a matrix. And that's it, right? It's like, it's going to be the easiest, what are they worth? Like 8% or something that you've probably ever heard. Because, like I said, these are all exercises that students genuinely don't have trouble with. Like, it seems daunting, and then everyone does it, and they're like, "Wow, that was really easy." But then that means in Wednesday's class and Monday's class is just a work period, so you can come work on that, or you can work on the final project, whatever. Or you can stay home if you want. Whatever. I'll be here either way. So if nobody shows up, I will still be here, and I'll be sad about it. But I don't think in all my years of doing this I've ever